All right, so welcome everyone. My name is Itzik Ben-Gan, and the session you're attending is about all kinds of workarounds to T-SQL restrictions, limitations, or kind of missing functionality, things that you would like to have in T-SQL, maybe that currently don't exist, maybe that will appear in the product someday. But anyway, I wanted to show what kind of workarounds you can use today for those missing features. Like I said earlier, if anyone has any questions, I'd be more than happy to take those. Please don't feel like you have to wait until the end of a topic or the session itself or anything. We have just 1 hour for the session, so I'm going to just check the QA section. There's no need to raise your hands or anything. Just go type whatever you need in the chat box and I'll respond there. By the way, when just something like an hour or two before the session started, my Wi-Fi at home was gone, and I checked. Apparently, there was an outage with my Wi-Fi provider. So you can imagine I was a little bit panicked, and I started trying to figure out if I can use my mobile hotspot. We also don't have very good mobile reception. I live in a rural area, and it kind of came back maybe 15 minutes ago. So I'm really happy that we should have good quality now for the delivery. So if anyone wants to download the source code for the session, it's already available in this website. If you go to tsql.lucien.com, you will find there a section called resources, and within it downloads, and you can download the source code for this session, my other session that I will have tomorrow as well. All right, so let's go ahead and get started. We'll see how many items we get through. I'm hoping to get something like 2, 3, maybe 4 items covered in the coming hour. We'll start with a row number function. So I'm guessing a lot of people here are regularly using window functions, including row number, rank, dense rank, and so on. The thing is, sometimes we want to compute those row numbers, but just in order to assign unique, kind of numbers to the rows. So if we'll take kind of a basic row number example, I'm quite sure that many of you here are regularly using window functions like row number. And, in many cases, you do need to compute those based on some ordering. So here, for instance, maybe I want to compute row numbers that are based on order ID ordering in this particular table. But probably also for you, like for me, there are some cases where you need to compute those numbers in no specific order. Yeah. So let me maybe here just show a few of the rows. So this would be an example where I'm computing them based on order. But what if I need just unique numbers? So you know that with the ordering aspect of our row numbers, so let me see, I just see a message from someone that it will be broken soon. My processor is crying for cold, and graphic cards is, okay, I see a message that there could be some issue later on, but just please let me know if at any point it becomes frozen again. We'll see what we can do with it. So at any rate, going back to what I started saying, if we need to compute row numbers based on some order, there needs to be in the execution plan some support for this ordered computation. So we have generally 2 ways for the optimizer to get the data ordered. Anyone has an idea? And please type in the chat box. What would be the 2 different options for the query optimizer when it needs to process data in order? What are the 2 ways for the optimizer to get it ordered? So I see already a suggestion ordered by Nal. You're already thinking about a solution for unordered row numbers. But I'm saying, let's take an example like this. I want to produce row numbers that are ordered by employee ID. Okay. For the optimizer, what are the 2 options to have the data be processed ordered? Yeah, one of course is to sort, but is there a way for us to prevent the need for sorting? What would be an option to have this processed in the right order, but not involve a sort in the execution plan? So group by would be just another querying element that can be handled either with an order-based algorithm or hash one. But I'm saying this very specific query. Can we avoid the need for a sort in the plan? This specific query you're looking at. How can you support query? Yeah, so I see one suggestion to create a clustered index. I would say not necessarily clustered index, but just a supporting covering index. Yeah, so if I create an index with employee ID as the key and with order ID as an included column, or like one of you suggested, so let's see, one of you suggested the clustered index, as long as it's covering, we can certainly avoid the sort. Now, currently, if we examine the query plan, we can see that the sort is happening, but that's just because I did not create the supporting index, right? So if I go ahead and create one, create index on employee ID that also includes order ID. Yeah, let's go ahead and create it. It can either be with the order ID as a second key, or since I don't really care about the order of the order ID element, I can always have it as an included column. So the basic idea is that either we prepare a supporting index, and then the optimizer figures I can pull the data pre-ordered from the index, and then basically avoid the sort. So let's have a look at the query plan and see that this is indeed what happens. Notice how it uses the index that I just created. You can see it pulls the data ordered from the index, and therefore you do not see any sorting happening before the actual computation of the row numbers. But clearly, if I do not have a supporting index, there is no escape for the optimizer, but essentially to introduce a sort operation in the plan. Close the shade here. I'm just asking my wife to close the shades because I'm getting sun in my eyes. Sorry. So anyway, so here we have a basic row number computation. When the row number computation needs to be done based on any specific order, then basically you need some ordering support. And a couple of you had the correct answer when I asked about this. Either you need a supporting index, covering index, unclustered or clustered, or you need a sort in the plan. And the reality is that sometimes you just need to compute row numbers that are not ordered by anything specific, because the only reason for computing those row numbers is to create unique values for the rows. And then you don't want to pay any unnecessary penalties, right? You don't want certainly a sort, but you also don't want to need to organize any form of an index. And even if you're saying, but wait a minute, can I not put order by, you know, whatever is the clustered index key? In this table, the clustered index is an order date. Can I not just say, okay, I'll say order by order date, and then surely the optimizer would use the any index on the date. The thing is, this is a very simplistic query. And sometimes it's actually more often than not that the queries in real life are much more elaborate, and they involve already a bunch of joins and filters and whatnot. So it's not always that straightforward to come up with the right ordering that would avoid a sort. And even when you have a simple enough situation and can specify something that is supported by an index, we are limiting the storage engine to using an ordered scan of an index as opposed to not requiring an ordered scan of the data. This is all to say that we really need a way to somehow say, I want row numbers that are not ordered. But when you try it, you get an error saying no, an order by clause is mandatory. And then it gets really fun when you try to get around this restriction. Because the first attempt, actually one of you suggested, how about if I say order by null? Yeah. So notice there is an error message saying, hold on, you cannot use a constant here. They expect you to rely on an expression because they know that the constant would represent the same value for all rows, and then it won't be real sorting, right? So if I try maybe instead of a null, maybe a 1, it actually thinks that this 1 is an index of an expression within the select list. So you can see the error message is slightly different than, you know, not supporting a constant. But if it's a, like a null, basically, it goes back to the error message with a constant. Now, what if you try to be smart and you say, okay, so if it expects an expression and not a constant, what if I did this? Anyone has an idea what's going to happen? And I see already one of you is suggesting a solution, and soon I will get to why this suggestion of order by and then subquery with select one works. I'll soon get to why it works, but anyone knows what's going to happen now when I'll say order by and then some expression, which is what it's expecting? Anyone here heard of a concept called constant folding as part of query optimization? You know that the optimizer, before it starts to handle the full-blown optimization, a very early stage of the query processing, it tries to simplify things that could support, better optimization. For instance, if it sees expressions can be folded into a constant, it usually folds those. So this internally, in the early constant folding phase, becomes a 2, basically. So if I try running this, you will see the very same error message that we got before when it thought that we were specifying an index of an expression in the select. And the same thing with a constant. So if I say a plus b as an expression, constant folding, will result in ab, and the very same error message that we saw before, constants. Now, we now try to kind of work around this constant folding situation, even though in most cases, constant folding is a very good thing for us. Here, it prevents us from getting what we're after. So we want to try and employ some kind of a trick that will prevent constant folding. Anyone knows what elements in the code prevent constant folding? And if I had a bottle of schnapps now, anyone who gets the right answer would get a shot now. So what would be things that prevent constant folding? So I see one suggestion is to use a subquery, and that's very, very true. Generally, if in your query you embed a subquery, this indeed prevents constant folding, but still looks like an expression to a T-SQL. So if I'll in a subquery say select null or select one or whatever, this actually works, yeah? So notice, if we check the query plan, this is a valid query. Notice it just picks whatever index has all of the data. Could be the clustered index, could be any index that has all of the data. And you can also see that it does not expect to pull the data from the index ordered by the index key. So we leave the storage engine with the full freedom to choose, to apply what's known as an allocation or the scan if the right circumstances allow it. We don't force an ordered activity, and definitely there will not be a sort in the plan. So very good. This is one option. How about any other ideas how to prevent constant folding? What else, for anyone here who is familiar with the idea or understands the idea, what other things other than a subquery could prevent constant folding? Let me see. Some function call. Okay, so I see one idea is a function call. So I mean, it's true that the function call, even if it represents what's known as a runtime constant, yeah, I could call, for instance, at speed to get the session idea. This is what's referred to as a runtime constant. What's interesting, it's not really related to prevention of constant folding, but rather this is just something that looks to a SQL Server like an expression, but at the very beginning of the processing of the query, first gets converted to the constant and then used as the same value for all rows. So we indeed achieved the very same goal of making it look to a SQL Server like an expression, but still knowing that it's the same value for all rows, it will know that it doesn't need to sort. So yeah, notice this is a valid query. And again, we're back to a plan that can pull the data ordered false and not require sort. So excellent, you're getting a snapshot, okay, for this. But here's another very bizarre thing. How about this crazy idea? If we write an expression that results in an error, you realize that the constant folding phase will not succeed, right? So how about if I did this? If I wrote an expression like dividing something by a 0, clearly this cannot succeed. And if it ran in actuality, of course, the query would have failed. But the bizarre situation that develops here is the early query processing phase of constant folding attempts to fold this expression. It cannot because it creates an error. So it just avoids the constant folding phase, but then it proceeds to the full optimization. And in this full optimization phase, it realizes, hey, it's an expression made entirely of constants. Therefore, I don't even need to run it. I just know that it's the same value for all rows, and then I don't need to sort. So unbelievably, this works beautifully, and we achieved basically the goal. Now, to tell you that I recommend using this technique, unless you're really drunk, I will say absolutely no. So it's kind of cool just to know how the engine works and how optimization works and what things, can get you what you're after. But say that I feel comfortable with this technique, I will say not so much. I would still recommend going with one of the earlier techniques that I feel that are safer. But again, like I said, it's just very kind of good to know how things work behind the scenes. So my personal preference, I can tell you, is usually to go with the select constant. And because you hear so much kind of objection to using nulls, there will be those relational modeling purists that will tell you never touch a null, this is a bad thing, this is the worst thing in the world. That's one of the reasons why I like to actually say select null just for spite. Otherwise, another kind of very, very curious thing is, anyone here ever stumble into a case where you optimized a certain query and you needed to prevent parallelism? Ever happened to you? Yeah, sometimes parallelism is of course a very good thing, but there are certain circumstances where the query actually ends up getting a parallel plan, and you know that in this situation that's not a good thing. Now, obviously, there's always the option here to add option max.1. But there are certainly cases where you prefer to do this without forcing it with a hint, in scenarios where a hint is not a possibility or not the right permissions or whatever. Yeah. So curiously, and that's something I learned from Paul White. Maybe some of you are familiar with Paul White from New Zealand. He knows query optimization, I think, more than anyone else in the world. So I learned from him that when using a runtime constant in the form of a function, when you use certain functions, they do not prevent parallelism. So, for instance, at speed, there's nothing special here with parallelism. But when you use specifically the train count function, as it turns out, there's some internal technical reasons why Microsoft chose to do so. But apparently, this is a parallelism inhibitor. So, if you have a combination of I want row numbers in a specific order and where this code appears, you also need to prevent parallelism, you just choose this specific runtime constant. So I can tell you, I relied on it. It was really fantastic to know that this is an option. All right, so I will strongly recommend using one of the kind of safer techniques, like what I do with the select null option. All right. Now, moving on, I'm going to continue to the second trick that I wanted to show, and this has to do with something I stumbled into recently when I wanted to create an inline table valued function that produces a sequence of numbers, kind of similar to a generate series function that you have in Postgres. We'll see later if we have any time left to also talk specifics about this function, but first, just another technical aspect that is tricky in T-SQL, and I wanted to show a workaround of how to resolve it. So let's look at the situation where we need to compute something and then also order by that computed element. So have a look at this very basic query. Currently, I'm not applying any manipulation to the order ID column. I'm just showing what happens if I assign an alias to an expression and then order by the alias. There are certain situations where the optimizer says this, even if it's not an actual column from the table, this represents an expression that is order preserving with respect to the original column that appears in the expression. Why is this interesting for us? Because if the optimizer sees that in the plan we carry this ordering property of the original column, then it knows I can rely, again, on indexing to avoid a sort in the plan. So if anyone here wants to type in the chat box, yes or no, how many people think that if we have an index on order ID, and we do, we will see a sort in the plan? How many people think that you will see a sort in the plan despite the fact that there is an index? Yes, no, please. Yes for sort, no for no sort. Okay, so everyone who says no gets a virtual snapshot, and I see only one who says yes. You get 2 snapshots because you're wrong. But anyway, here, like I said, this is an order preserving expression. The optimizer easily figures this out and avoids a sort. So let's go ahead and look at the query plan. And as you can see, we are obtaining the data from the index on order ID. It's called PK orders, and you will see that we pull the data order true, basically meaning that the storage engine will follow the index linked list and avoid a sort. Now, let's do this. What if I need to add a computation here? Perhaps I need to do something like this. Now, here I'm using constants, but you can imagine that those things are relevant when you have parameters that you pass to a stored procedure or maybe a user-defined function, and you need to incorporate those parameters in the code, okay? Now, what's going to happen? Again, yes, no. Will we see a sort within the plan? Yes, no, in the chat box. Will we see a sort in the plan? Wow, I see everyone says yes. Okay, so let's have a look at the query plan. And indeed, we see a sort. But wait a minute, if I do this, let's check for a moment the query plan. And as you can see, for the optimizer, it clearly figures, wait a minute, this is the original column that has ordering support via an index. This is just a constant. Well, I don't really need to sort. So if this doesn't produce a sort in the plan, any ideas why this does produce? I mean, why don't we get constant folding here? Let's see if anyone has an idea. Why do we not see constant folding like we saw before happening? Because clearly, if constant folding took place, this would become the constant one, and we already saw that with just a constant, it's going to avoid a sort. So any clue why this is not experiencing constant folding? This is a little bit tricky, but why? All right, so we don't have a lot of time left to the end of the session, so let me explain. Oh, I see someone typing. Let's see, Thomas is typing. What's the idea? Why do we not see constant folding? Too much operations. Well, I mean, kind of close. What you're saying is kind of close, but the thing is, this expression is evaluated first. Now imagine we call this expression expression 1. This is clearly not a constant. Now internally, there's expression 1 minus 1. And of course, now that this is not a constant, the optimizer doesn't realize there's an order preservation situation here. So anyone has an idea, based on what I just said, that this expression is evaluated first, results internally in something, and then this expression is evaluated second. How can we retain the same meaning but enable constant folding? Exactly. Fantastic. I mean, you would get an entire bottle of schnapps if I was there now. So the simple trick is put this piece first. And let's see what's happening in the plan. And here we go. There is no sorting. So, I mean, I can tell you this drove me crazy. Like I said, for a while I was working on a fast version of a function that produces numbers, and I'm passing to the function a low value and a high value to represent the boundaries of the range. And the function needs to involve 2 elements one with the plus sign, one with the minus sign. And when initially I had the column plus and minus, those two elements, whenever I try to order by the result column coming back from that function, I kept getting a sort, and it didn't seem to make any sense until I found out that all I needed to do is just place those two elements at the very beginning. Now, let's see how this is important within a function. So we encapsulate the logic within a user-defined function. Take here, I'm just showing a very simplified version of the function, but remember, the original case where I found this was in a function that generates a series of numbers, same kind of situation. But here, let's say that we have a function that gets two input parameters, an add parameter and a subtract parameter. And as you can see, it now uses a kind of a parameterized form of the earlier query. So if we specify column plus add minus subtract, this will not be an order preserving expression. Now, if you're thinking, wait a minute, but this is a function and these are parameters, they're not really constants, what the heck are you talking about? Well, this is an inline table valued function. You notice this is an inline table valued function. So when you call it and you pass constants as inputs, there is a process known as parameter embedding, where before the optimizer kicks in, there's first a process of replacing the parameters with constants. But here, we don't have any potential for order preservation due to the fact that constant folding will not happen, right? So let's try it. Let's create a function. Then let's go ahead and call the function passing a couple of constants. Now, remember what I said. When you use an inline table valued function, the parameter references are first replaced with constants. So behind the scenes, this inlining process results in this, right? And as you know, written in this order, we're not going to get constant folding. Let's see. Let's have a look at the query plan. Yeah, and observe, we ended up with a sort. Again, the computation, you can see here, the scalar computation, as you can see, does not fold this activity of 2 minus 1, and therefore the resultant expression 1003, becomes the expression for the sort activity. So again, like the earlier suggestion, how do we fix this? All we need to do is simply pass these two to the very beginning of the expression, and problem solved. Let's try. So again, if we try to emulate what the parser basically will do beneath the covers, what it will do when we call it like this will be put here a 2, put here a 1. Since this is the first expression now, there's first the constant folding happening. This becomes a 1 plus order ID, and the optimizer says, hey, this is an order preserving operation. We can safely, go ahead and do avoid kind of a sort. So let's see that indeed that's what's happening beneath the covers. Let's have a look at the query plan, and boom, no sorting. Have a look at the compute scalar operation. What will be behind this expression 1003? This is, notice, folded value. You see this? 1 is already after the folding of the 2 minus 1, and therefore we get order preserving. Yeah, so there is a question of what happens if we add more parameters. This would be basically very similar to doing this. Yeah. And observe, when we look at the query plan, no sorting, because it still gets constant folded. So okay, again, there are many questions about what if we use brackets and so on and so on. Try it. Generally, as long as all of the constants appear one after the other and at the beginning, this is what will get the optimal treatment. So the general recommendation for what you see here is simply make sure that you do all of the operations on all of the parameters at the very, very beginning, and then add or do whatever you need to do later with the column. Also, another critical point to emphasize here is that this happens when you use an inline table valued function. Anyone has an idea whether we will get the same treatment if we use the store procedure? Again, yes, no, in the chat box. If we had the very same query in a store procedure instead of an inline user-defined function, would you see constant folding happening here? No, because the parameterized code is the one that gets optimized. Now, there is one exception. Anyone can guess, or not guess, but an educated guess. What would be one exception when the code resides within a stored procedure, but you still get constant folding happening even though you're using parameters? One exception. With recompile. Fantastic. But that's when you use a recompile at the statement level, of course, not the procedure level. So if this was a query within a stored procedure, yeah, then simply by adding, I mean, of course, this has ramifications in terms of paying the cost for the optimization and so on, but as long as this is acceptable, when you say option recompile, again, first, we get, actually, this is not the function call. What I meant is, of course, this. If this is your code within the stored procedure, then you add option recompile. Again, first we get parameter embedding. This is treatment that is very similar to an inline table valid function, but of course with the extra cost of the recompile, where first the parameters are replaced with constants, then any constant folding, if it can happen, it happens, and of course then a real full-blown optimization starts. So this is, I can tell you, for me, very new. I didn't realize things were like this, but since very recently I was doing some work on trying to generate an optimal numbers function, and for a while earlier, I sometimes saw a sort in the plan, sometimes I didn't see a sort in the plan, and I couldn't make the connection, but apparently some of my implementations had parameter plus column minus parameter, and some implementations had parameter minus parameter plus column. And back then, I just didn't make this connection. All right, so let me show you where this becomes very, very relevant in this real-life situation. So I'm betting that many of you regularly need some kind of a function that generates numbers for you, where you can go ahead and tell it, select the number from my function, then you pass some, a range of numbers that you want. You know that in Postgres, they do have a function called generate series that does precisely this, and it would be fantastic if one day we get to see such a function in SQL Server. So basically, some months ago, I started this project of trying to get the SQL community involved, or the SQL Server community involved, in creating the best performing numbers function that we could come up with. Yeah, and this I don't know if anyone here was aware of this or participated in this, but this was a beautiful project where I got many suggestions, and I kind of collected from the different suggestions the kind of best ideas until we ended up with a function that is kind of unbelievably fast. But one of the techniques that I ended up relying on was, first and foremost, you need to come up with some kind of a way to generate a large number of rows. Because what if someone is asking for 1 billion, numbers? I wanted the solution to be flexible enough to generate up to at least 4 billion numbers if you need to. So the first kind of challenge is, how do we create a large number of rows? Then, as a second step, we can worry about producing those, numbers themselves, right? So anyone can think of a tool in SQL that can very quickly generate a huge number of rows, some kind of an operator. Yeah, so I see one suggestion here, city plus cross joints, fantastic. So this is indeed what I ended up using. So first we start with generating some base sort of a table that has a certain number of rows, and then we can start doing cross joins, right? So you could use a values clause to generate this base, and I can tell you I did a lot of performance experimentations, both in terms of performance of the cross joins themselves, as well as we also need to worry about compilation time. Yeah, so you could think, and I've even seen such solutions where people generated the base table expression with 256 numbers or rows, and then started cross-joining, but then the values clause, when you generate too many rows with it, imagine this with 256 rows, there's some complexity in the compilation process that has exponential scaling or exponential complexity. So this is actually a very bad idea to use as a base table expression, a very large one. So after doing a lot of performance testing, I found that a base table expression size of 16 is ideal. So that's what we do. We take the values clause and have 16 rows with any constant. It doesn't really matter, yeah? So let's do this 16 times. So 1, 2, 3, 4, 5, 6, 7, 8. This would be 16 rows, right? Now, we put this in a derived table definition. Let's give it a name D, and let's call the column C. And now we can say select C from this basically derived table. As you can see, what we got, notice, is 16 rows. Yeah, 16 rows. All right. So now, if I want to figure out how many cross joins I need to generate, let's say, 4 billion rows, we can use a formula, but I can tell you that just starting to do a series of cross joins is not going to be a very small number. So what I realized is that I could have now kind of a series of cascading CTEs, where this would be the base CTE. Maybe we'll call it level 0. Level 0 is the first CTE, the base one. Then have a second CTE, let's call it level 1, that goes and creates a single cross join from level 0. So level 0, let's call it A, cross join, level 0 as B, okay? So essentially now we're getting 16 squared. And now you realize that if I proceed like this with a second CTE and then a third CTE, so level 2, when it will apply this logic to 2 instances of level 1, it's 16 squared, and then this number squared. And then level 3 will add another square to the result. All right, so there is a formula. It would be fun to write it with T-SQL, where you do power of the base CTE size, which in our case is 16, raised to the power of 2 to the power of the number of levels that you are creating. This will give you the total number of rows that you will produce here, right? So in our case, the number of levels in this scenario is 3. And as you can see, this is the 4 billion rows that we try to achieve. So what you see here, if I actually did a select from L3, I'm going to get this many rows, 4 billion. So this is way more than enough, agreed? Now, what would be the next step? Remember, all of this will reside within an inline table valued function, right? So here I'll just create 2 local variables. Later we can convert them, to the function. So the low value, let's say, just as an example, starting 101 for this particular execution, then the high value, right? So we have now one more step where we need to generate the actual numbers. Now we start with just numbers starting with 1 and on, and later with the calculation that involves these 2. And I'm guessing already some of you have a kind of a light bulb turning on in your head, connecting the earlier discussions that we had about row number with no ordering and the constant folding to what we're about to do here, right? So here I'll go ahead and generate numbers CTE that is basically a sequence of all 4 billion, potentially all 4 billion row numbers, right? So select from the last T, and then how do we produce those numbers with a row number function, right? But what do we order by? Don't really care about any particular column, right? We don't want to see any sort penalties, but we already have an answer for this. We order by course, a subquery that returns a constant, right? So now what we're getting back is a row number column. And what's left for us to do, the very, very last piece, is now we need to produce the sequence of numbers that the user is requesting, right? So this would be select, and then if we do this, select a low or row num from nums, order by row num, and here say select row num a plus low minus high. Actually, sorry, I'm supposed to say plus low minus 1. This will give us, of course, the numbers themselves. Let's call it n. But then we will want to somehow restrict it to the requested number of numbers. So here we need a top that then goes and says, take high, subtract low, and then add a 1. Yeah. If we write like this and encapsulate this in a user-defined function, you realize that later when we select from the function and say order by n, we will end up with a sort penalty. So what we do to fix this is simply take this, make sure that we put it at the very beginning of the code, and then add the row number. And this will both produce the correct result, and when encapsulated in a use-defined function, when we'll do a select and pass constants as inputs and order by n, will not incur sort penalty. So first of all, let's see that this produces the right result. As you can see, indeed, it produces the right result. Now, if we go ahead and put it in an inline function, passing these two guys as inputs. So we'll set the default start point to 1 and not assign a default start point at all here. Say returns table, then as return this thing. Then go ahead, close the function. Now we have our get nums function, or we don't. Let's see. Yeah, I have the declare above. Okay, so now we have our function. Now, whenever we want a sequence of integers, we say select n from get nums, then pass whatever you need as input. So first of all, observe we're getting the right stuff. Now, if we need to consume this result order, then we say order by n. This is where we have the connection to the discussion we had earlier about the avoidance of the sort. So here we had this trick to not require a sort for the row number itself, but here we had this trick where we started with the input and the constant and then the column, and this way, if we have a look at the query plan, as you can see, absolutely no sorting that is needed. There's first the cascading CTEs that are cross-joined, and then you can see the computation of the row numbers and top applied based on this order, but it knows that it's meaningless order, so it doesn't really need to involve any sorting. Yeah. Now, this is not yet the final version of the function that I ended up using, but it's already fantastic in terms of the performance that it produces. So if we go ahead and check its performance, let's maybe take it aside. Okay, then what I'll do is I'll assign the result to a variable. And this is just, of course, to avoid the time it would take to print the numbers in the result. And then ask for, let's say, numbers between 1 and, say, 1,000,000. Yeah, let's see how long it takes. Not too bad. Yeah. Not too bad. But still, you know, it's, as you can see, 1 second. If we go up to 10 million, okay, let's see how long it takes. Okay, so as you can see, this got to 16 seconds. And if you want to measure including the actual delivery of the rows to the caller, we can right-click an empty area in the query window, go to query options, go to grid, discard results after execution, and then not assign it to any variable. And now what's happening is the rows are indeed transmitted to the client, but it doesn't print those in the Management Studio screen because we discarded results. So depending on what kind of performance you want to measure, if it's something that needs to be transmitted to the client or not, just engine processing, you would choose one testing technique or the other. So, I mean, it's not bad performance, but we can still, as you can imagine, do better. And what's really missing in this specific case, if we examine the query plan, yeah, let me just show you the query plan. I'll copy it maybe to a separate window, and we can go back to the previous. Here, you can see 29 seconds when we include the transmission of the rows to the caller. So if indeed we are after a test that only checks the engine processing kind of effort without the transmission to the client, you would use this testing technique. Have a look at the query plan. Does anyone have any idea, for instance, if we look at the row number computation, of what could still substantially improve the performance of this code? Certain kind of processing that is fairly new, a new processing engine. Anyone think of a way to further improve the performance of what we're seeing here? Anyone think of a new execution engine that was introduced along with another technology some versions ago? Batch mode, thank you very much, batch mode. Why are we not seeing batch mode here? Why no batch mode here? Why are we not seeing batch processing used here? What kind of indexing are we missing currently on the data? I mean, there's no data we're really querying. Yeah, no aggregation, no column store. Excellent. So if we involved a table with a column store index in a query, this would enable batch processing. So here's what we're going to do. We'll create a table. Okay. And then go ahead and create a column store index on it. So now we have a table with a column store index. Now we need to embed it in kind of a meaningless way in this query. So what we could do, for instance, is add here a meaningless left join with our column store table with a condition that is never true. And as long as we don't touch any columns from this table, it doesn't even need to be physically accessed. You realize, yeah? So let's recreate our function and go ahead and check the query plan. And here we go. Here's a row number computed with the batch mode window aggregate operator, yeah? And then we can go back and check the performance of our request for. Actually, let me go ahead and stop the showing of the execution plan. Yeah, let's go ahead and run this. And I remind you that earlier it was, 16 seconds, I believe, that it took to complete? Okay, so of course this always happens when you test something and try to demonstrate, but I can tell you that in experiments with 100 million rows, I got quite substantial improvement in performance. And by the way, that's not the end of it. So if anyone is actually interested in seeing this complete discussion with the community, with all kinds of suggestions and further improvements beyond what you see here, go and check out SQL Performance, SQLperformance.com. I have a monthly column there, and you will see a whole series about the kind of number series generator challenge, and you will see first one article with a challenge, and then a series of 5 or 6 additional articles, and showing performance comparisons with further tricks that can make the entire plan a fully batch mode processing plan. So anyway, this is pretty much what I had to say. I'm really happy that we somehow managed to get this to work. So I really appreciate it. And Dan, are you still there? Dan, still there?
Yes, I'm still here.
Oh, I'm so grateful for coming up with this idea of the Zoom. You kind of saved the session. So thank you.
It's my experience.
So you went through the bad experience and you saved me. I really appreciate this.
You're welcome.
All right. Thank you, everyone. I hope you enjoyed the rest of the conference. I understand that we have a panel coming next. I will be there as well if there will be any further questions. So happy querying, everyone. Thanks for attending and enjoy the rest of the conference. Take care.